Hi, welcome to Problem Solving Experts. In previous videos, I have talked about evaluating the performance in terms of sigma. If our sigma is smaller than 2, we are having a very big problem. If it is between 2 and 3, we are having a big problem. 3 and 4, medium-sized problem. 4 to 5, small problem. And more than 5 sigma, there's not any problem. And the sigma is highly correlated with DPMO, defects per million of opportunities, and we are going to use that one when we are having attribute type of metric, or PPMs, parts per million, which is the one that we are going to use when we are having a continuous metric. Well, PPM, parts per million. What do the PPMs represent? What we have said is that is the probability to be outside the specification limits. And how to calculate that probability? Also in a previous video, I have said that that is the proportion of the area below the distribution curve that is outside the specification limits. Well, the question is, what distribution curve? I have also said that there are two types of distributions, normal distribution and non-normal distribution. For a non-normal distribution, there are many types of other distributions. But in this video, I would like to talk a little bit more about the normal distribution. So basically, this video is about normal distribution and how to deal when you are not having a normal distribution. And well, the first option is basically try to normalize a non-normal distribution. Let me start with that. First, normal distribution. What I have said is that that is the most frequent distribution that happens in nature. That is also the most frequent distribution that happens in processes. And because of that, that's why we talk about a lot about the normal distribution. Some characteristics about the normal distribution, I have said in a previous video that this is bell-shaped. Second is that this is symmetric. So this is like a mirror of this other side. The left and the right side, they are both exactly same shape. They are symmetric. Asymptotic, that means that the distribution never touches zero. It's getting closer and closer and closer to zero, but never will touch zero. There always will be the probability of having something. And the inflection point is at 1 standard deviation. Basically, from the center to the inflection point of the curve, we are having 1 standard deviation. Keep in mind that the inflection point of the curve is where the direction changes. So you are having a distribution like this one, and then it changes the direction. When the point where it changes the direction is known as inflection point, and that distance is 1 standard deviation. Well, that's what I have said before. But now I would like to add one more thing, which is very important because that is key for the calculation of PPMs. And that is that the areas below the distribution curve are very well characterized in terms of number of standard deviations from the center. For instance, from the center, plus minus 1 standard deviation, this area here below the distribution curve is equal to 68.27% of the area. For instance, the mean plus minus 2 standard deviations, this area below the curve is 95.45% of the area. And well, the mean plus minus 3 standard deviations is, for instance, 99.73% of the area. So the areas are very well characterized in terms of number of standard deviations. So if you are having a normal distribution, all what you have to know is where is the mean and how big is the standard deviation. And from there you can calculate the area for that normal distribution. Let me explain that with one specific example. Let's say that this is my average sleep time. How many hours I sleep per night? and my average is 7.5 hours, and I'm having a standard deviation of 0.5. Well, we also for this metric are having a lower specification limit of 7 hours of sleep. That is the minimum that you should sleep per night. and a maximum and upper specification limit of 9 hours of sleep per night. The question is, what is the probability of sleeping less than 7 hours and more than 9 hours per night? And with that we will be calculating the PPMs, and also we will evaluate if I'm having a problem in terms of not enough sleeping time. So, well, all what I have to do is basically first calculate from the center to the upper specification limits how many standard deviations I'm having. So, well, let me do that here. I will do the area again here. I will do the distribution here again, and well, I'm having the mean here, and I want to know, and also let me say that I'm having a upper specification limit here. So this is my upper specification limit. The question is, how many standard deviations are there between the mean and the upper specification limit? That value will be known as Z upper. Z upper are the number of standard deviations that fit between the mean and the upper specification limits. Okay, see, Z upper is equal to upper specification limit minus the mean divided by the standard deviation. So this distance, which is the upper specification limit, which is equal to 9 hours of sleep per night, minus the mean is 7.5 hours of sleep per night, divided by the standard deviation, and the standard deviation is 0.5. That is equal to 2.5 divided by 1.5 divided by 0.5. And that is a Z upper equal to 3. That means that the distance between the mean and the upper specification limit is equal to 3 standard deviations. Well, with that I can estimate, or I can calculate in fact, how big is the area above the upper specification limit. I can calculate how big is this area. I can calculate how big is that area. And well, basically I can get that one from here. As we can see here, the mean plus minus 3 standard deviations, that is a total area, the mean plus minus 3 standard deviations is a total area of 99.73%. That means that, and because that is symmetric, that means that half of this 99.73% will be from here to here, and the other half will be from here to here. So half of that 99.73% is equal to 49.865%. That is half of 44.73. The mean plus minus 3 standard deviations, 99.73. Because symmetric, half will be 49.86 and half will be 49.865%. That will be the other half of the plus minus 3 standard deviations. That means that the area outside is 0.27%. And of that 0.27%, half will be at the right and half will be at the left. That means that the area here is equal to 0.135%. And that is the area. By the way, if you add this plus this, that is 50% of the area. Keep in mind that this is symmetric. And symmetric, 50% will be right side, 50% will be left side. Then this area is 0.135%. In terms of parts per million, that is 0.135 in 100, 1 in 1,000, 13 in 10,000, 135 in 100,000, and that is 1,350 in 1 million. So the parts per million will be 1,350 parts per million, which is the probability of being above the upper specification limit. Okay, let's repeat the same mechanics. Let's do the same thing, but for the lower specification limit. The mechanics is the same. So we have to establish our lower specification limit, which is here. Here is our lower specification limit. We have to calculate the number of standard deviations that fit between the mean and the lower specification limit. We will call to that one Z lower. And then we will have to calculate this area, the area outside, below the lower specification limit. This is the lower specification limit. Same mechanics. What we have to do is to calculate Z lower. The Z lower is equal to the mean minus the lower specification limit divided by the standard deviation. That will be Z lower is equal to the mean, the average is 7.5 hours of sleep, minus the lower specification limit, which is 7 hours of sleep, divided by the standard deviation, 0.5 hours of sleep. Then that will be 0.5 divided by 0.5. Then Z lower is equal to 1. That means that from the mean to the lower specification limit, there is one standard deviation. This size is in terms of the standard deviations, or this distance is in terms of the standard deviations. Well, we will use the same thing. We know that the area is characterized in terms of number of standard deviations, the area of the normal distribution. Then, from the mean plus minus one standard deviations, the area is 68.27%. So, from the mean plus minus 68.27%. That means that half of that will be here, and half of that will be to the right. Half of that 68.27% is 34.135%. That is half of the 68.27. So 34.1 will be here, and 34.1% of the area will be here. If you keep in mind that 50% of the area is below the mean and 50% of the area is above the mean, then the area that we need to complete the 50% here is something like 15.865%. So this area is 15.865%. That means that this is in terms of percentage. In terms of ppms, that will be 15 in 100, that will be in 1,000, this will be in 10,000, in 100,000, and in 1 million. So the area is 158,650 parts per million. So the total ppms basically is ppm total is equal to ppm lower plus ppm upper. So the total ppm is equal to 158,650 plus 1,350 parts per million. The total parts per million is, 160,000 parts per million. Which is 158, 59, 160,000, which is basically 2.5 sigma. If you can take a look to the sigma value and the PPMs, 158,000, very close to will be the 2.5 sigma. And that's how we will have calculated the PPMs when you are having a normal distribution. Well, as I have said, it's relatively easy to calculate the PPMs when we are having a normal distribution, because the area of the normal distribution is very well characterized in terms of number of standard deviations. Well, but what about if we are having a non-normal distribution? There are also techniques and ways to calculate PPMs for non-normal distributions, but the first option is to try to normalize the non-normal data. And the reason of that is because I have said it's relatively easy and very accurate to calculate when the PPMs when we are having a normal distribution. So for instance, if we are having a distribution like this one, which is a non-normal distribution because, as you can see, is not symmetric. One of the characteristics that I have said, that I didn't say about the normal distribution, is that the mean, the median, and the mode, all of them are at the center. But in this example, we will see that that is not the same situation, because you will see here that the mode very likely is here, which is the most frequent value. Here will be the mode, and here you will see that here you are having the median, for instance. Maybe the median is here, and well, perhaps you are having the mean here. Let me say that here you are having the mean. So one is not symmetric, and by the other hand, the mean, the median, and the mode are not at the center. So certainly that is not bell-shaped. So certainly that's not a normal distribution. Then what should we do? The first option is to try to transform the data. So perhaps if we can find a transformation that will normalize the data. I mean, we are having the original data, which is not normal, and somehow we transform the original data. So the transformed data will become a normal distribution. For instance, for a distribution like this one, the first option that comes to my mind is to square the terms. So you are having your original data, and if you square each of the values, very likely the square, the values square will become a normal distribution. So here, basically, what you will do is, basically, you have your transformed data, and your transformed data will be your original data square. And if you do that, then very likely it will become a normal distribution now. And well, the mean, the median, and the mode, they are at the center. This is symmetric, bell-shaped, etc., etc. Also, what you have to do is to square to the specification limits. Keep in mind, this is the lower specification limit, this is the upper specification limit. What you have to do is lower specification limit, square, and you will have the square lower specification limit. And also you will do the upper specification limit square, and that will be the upper specification limit square. And then you have to calculate the areas above the upper specification limit, below the lower specification limit, for a normal distribution for transformed data, and the transformed data will be the square terms. Or for instance, if we are having something like this, for the first one we are having a tail to the left, but if you are having a tail to the right, Perhaps the best distribution is to square root the term. The original data is not normal, but if you square root the original data, the square root of the data very likely will become a normal distribution. So, well, we are doing the same mechanics. For instance, what we have to do is that the transform data is the original data square root, and let me do exponential 0.5. And with that, well, that will become very likely a normal distribution. What you have to do also is to square root the specification limits, the lower specification limit, the square root, the upper specification limit, the square root, and with that you will calculate the areas for the normal distribution below the normal distribution outside the specification limits square root and the original data square root. So and that will be your PPMs. Same thing for this one. For instance, if you are having exponential distribution, this is known as an exponential distribution, well, maybe the best transformation for an exponential distribution is logarithmic. So, well, basically, same thing. You will have the transform data, which is the log of the original data. And for the log of the original data, it can become a normal distribution, and also the specification limits log, that will be lower specification limit, for instance, transform, upper specification limit, transform, for instance, and that same procedure. Or if you are having something like this one, which is also a tail to the right, but there is a very big kurtosis, is very big peak here. If that is the case, perhaps the best transformation, it can be the original data and 1 over the original data. And that means, for instance, the original data exponential -1. And well, that will become very likely now to a normal distribution. And for that one, also you have to transform the specification limits doing the reciprocal process. I mean the 1 over the lower specification limit, 1 over the lower specification limit, and well, let me do here, because it will be lower specification limit, transform, and same thing here, upper specification limit, transform. So, well, that process, in fact, that is a technique, and that technique is known as Box-Cox transformation. And basically, the Box-Cox transformation states that the transform data will be equal to the original data exponential lambda. And usually, well, several lambda values are tried. The most frequent values for lambda are values that they go from -5 to +5. So several values of lambda are tried: -5, -4, -3, -2, -2.5, -1.3, -1.1, +1.2, +1.3, +3.5, etc. Several values for lambda are tried, and well, the normality test is checked for each of them. And by the way, now I would like to talk about normality test. I have said that probability of not meeting specification limits to be outside the specification limits, those are the PPMs. And that probability is calculated by the areas below the distribution that are outside the specification limits. Question, what distribution? Well, if it is a normal distribution, the area of the normal distribution that is outside the specification limits. And those areas are very well characterized in terms of number of standard deviations. Well, so the first thing before calculating PPMs, once that you have representative data, once that you have your specification limits, then you have to evaluate if you are having a normal distribution or not. Then you are going to run a normality test, or you should run a normality test to confirm if you are having a normal distribution. The most frequent normality tests are when you are having very few values, very few data points, you have to use a non-parametric test, and the most frequent one is Kolmogorov-Smirnov test. But of course, if you are having more data between 16 and 50, by the way, at that industry level, that is the most frequent situation. You take a representative sample, and usually is from 16 to 50 values. Then the normality test to use will be Anderson-Darling. That will be a recommendation. But if you have more than 50 values for research, for investigation, etc., I would prefer to use chi-square test. All of them are hypothesis tests. Those hypothesis tests, basically, they evaluate the null hypothesis is that the history. Let me put that in not in a statistical way, but in a more, let's say, practical way. Basically, the null hypothesis is that the histogram is not exactly like that, but this is just a concept, is equal to a normal distribution. And the alternate hypothesis is that the histogram is different than the normal distribution. Normal distribution. So all of these tests, basically you will, if you reject the null hypothesis, then you will confirm, you will accept that you are having a non-normal distribution. And then, well, what you have to do, or what you can do, is to transform, to find the transformation that normalizes the data, or deal with the data as a non-normal data. In a different video, in another video, I'm going to talk about how to deal with non-normal data when you were not able to normalize the data. Then for sure you can conclude from all those tests that you are not having a normal distribution. And of course, if you do not reject the null hypothesis, you fail to reject the null hypothesis. So what you have to say is that we do not have enough statistical evidence to conclude that we are having a non-normal, normal distribution. Then we will assume that we are having a normal distribution. So you never should say we are having a normal distribution, because in reality you never will know that. But you can assume that you are having a normal distribution if you fail to reject that you are having a normal distribution. Anyways, for practical terms, we will assume that we are having a normal distribution if you do not reject the null hypothesis. In reality, this is not what we are testing. In reality, what we are checking is the cumulated area of the histogram and the cumulated distribution. But well, I'm not going to go into the details of the statistics right now. How is the concept? How do I deal for all those three tests? The concept is about the same. The mechanics, the tests are a little bit different, some different, but the concept is exactly the same. So you are having a histogram, and then for that histogram, you will know the mean from the data. You can get the mean of the data, you can get the standard deviation of the data, and then you can overlay a normal normal distribution with that mean and with that standard deviation of the data, with the same mean and the same standard deviation of your data. So basically, for instance, if you're having the mean here and then you are having your standard deviation, then you will overlay a normal distribution, and then you have to compare if this bar is close to the normal distribution, if the center of the bar is close to the normal distribution, if the Markov class is close to the normal distribution, if this is close to the normal distribution, if close, etc. And if the distances are very small, if the cumulated distances, because I have said, as I have said, is cumulated area in reality, is small, that means that the histogram is fitting well to the normal distribution. But for instance, if you're having a non-normal data, it is clear here that his histogram is not normal because it's not symmetric. You have a tail to the left, so that's a skewed distribution. But well, you will have to do the same. You define where is the mean of the data, what is the standard deviation of the data, and then you will overlay a standard normality, a normal distribution. You will overlay a normal distribution for with that mean and that standard deviation. And you will do the same procedure. You will compare, well, the var with the curve, the var with the curve, the var with the curve. And of course, you will see that in some cases, the distance is very big between the center of the bar, the Markov classes, and the curve. So when you do the calculation of the distances, you will have that they are very different, than the histogram is not fitting well to the normal distribution, and then your conclusion is to reject the null hypothesis and accept that you are having a non-normal distribution. So well, basically that is the concept for all the three tests: Kolmogorov-Smirnov, Anderson-Darling, and chi-square. You will compare the expected areas with the observed areas, and then you will determine or the expected probabilities with the observed probabilities. And if they are very close to each other, you fail to reject. If they are very different, you reject. Then they are equal, and then you will conclude that that's a non-normal distribution. But now, what about if you are having not good resolution? For instance, sleep time. If you are having 5.5 hours, 6 hours, 6.5 hours, 7 hours, 7.5, 8.5 hours. So you don't have any value in the middle. You don't have anything like 7.23 hours, 6.85 hours. So you are having, well, in a previous video I have talked about resolution. You are not having good resolution. You will have a histogram like this one, and you will have many empty spaces or empty blanks. So well, if we try to use the same test, Kolmogorov-Smirnov or Anderson-Darling or chi-square, you will have to do the same process. So you will define where is the mean, what is the standard deviation, you will define the normal distribution, and then you overlay the normal distribution on the histogram. As we can see here for this example, apparently it's pretty normal. It looks normal because the distance of each of the bars to the normal distribution, the distances are not big. So you may or you should assume that you are having a normal distribution. But if you try to apply any of those three tests, your conclusion is going to be this one. The distance between this bar and this curve is small. But the distance between this center of this bar and this curve is big. This is small, but this is very big. This is small, but this is very, very, very big. This is small, this is big, small, big, small, etc. So at the end, you will conclude that the distances between the histogram and the curve are very big, and then you will reject that that's a normal distribution, and in reality that's a normal distribution, but you will conclude that that's not a normal distribution. Under that situation, you have to use Ryan-Joyner, which is using regression, different technique, not hypothesis testing, and that's the test to use when you are not having a good resolution. I have said that normal distribution is the most frequent distribution that happens in industry processes, in nature, in variables, etc. And that's one of the reasons of why it's important to talk about the normal distribution. Also, I have said that it is relatively easy to calculate the areas of the normal distribution, because the areas for the normal distribution are very well characterized in terms of number of standard deviations. So that's why, as much as be possible, when we are not having a normal distribution, I have already talked about what to do when we are having a non-normal distribution, well, how to check if we are having a normal distribution, and also I have said that what you can try is a Box-Cox transformation, finding a lambda value, which is an exponential, that normalize the non-normal data, will make them normal data. But sometimes you don't find a lambda value that normalizes the original data, which the transformed data will become normal. If that is the case, then we can try other much more sophisticated transformation. For instance, we can use Johnson transformation, which is not one transformation, but that's a family of 3 types of transformations. So, for instance, one of the families of transformation can be, all of them, by the way, are non-linear regression models. So those are non-linear models. So, for instance, you can do here that the transformed data, which we are trying to make them normal, to become them to be normal, is a coefficient b0, a constant, plus another coefficient b1 times the natural log of the original data plus coefficient b2 divided by coefficient b3 minus the original data. So you are having your non-normal data, original data, and you apply this model, this equation. Of course, you have to find what are the values of the coefficients, and once that you have the values of the coefficients, you apply that model, and the transform values that for the original non-normal very likely will become into a normal distribution. Other one can be this one. The transform is basically constant b0 plus coefficient b1 times natural log of the original value, which is the non-normal, the original data, plus b2, another coefficient, same thing. And another one, much more sophisticated, is b0 plus b1 times arc sin hyperbolic of the original data plus b2 divided by b3. Of course, as I have said, through nonlinear regression, you can get the coefficients, and once that you get the coefficients, you can apply those transformations. Very likely, in most of the cases you will have a normal distribution. But for few of them, they won't be normal. Most of the cases with Box-Cox transformation, they will become normal. And for most of these remaining cases, any of these transformations will make them normal. Still, it can be some very rare cases that Johnson transformation won't be working either, and under those situations, then we have to deal with non-normal data. In a different video, I'm going to talk about the non-normal data. Now, I would like to do a brief summary. Okay, now I'm going to summarize what we have seen after a few videos in terms of calculating performance. What I have said is that performance can be evaluated in terms of sigma value. If the sigma is small, we are having big problems. If sigma is high, we are having a small problem. And the sigma is related to the parts per million, the probability of having defects, or the calculation of number of defects that we are having, the ratio of defects that we are having. PPMs, parts per million, is the probability of being outside the specification limits. What is the procedure according to what we have seen to calculate those PPMs? First, you have to define the problem. Keep in mind that a good problem is made by 4 components: object, defect, extent, and impact. A good problem statement should not contain causes or solutions. Investigation shouldn't take more than 60 to 90 days, so that's why we have to define very well the scope of investigation. Once that you have defined your problem, then you have to define your metrics. We have said that you can have business metrics, and that's how we are going to measure the impact in the problem statement. And we are going to have technical metrics. For the technical metrics, you can have primary metrics, the ones that you want to improve, and counter metrics or secondary metrics, the ones that you don't want to make them worse, the ones that you want to keep an eye on them to make sure that they won't be affected. Once that you have defined your metrics, then you are going to collect data. If you can collect data by yourselves, that's great. If not, you have to rely on someone else. You have to create a data collection plan. Once that you have done that, the next step is to check if your data are representative. We have talked in a previous video about outliers to identify if you are having special causes of variation. You also can check if you are having the period of time is representative of current situation, is big enough to capture all the variations that happen in the process. Also that you have to check if you are having good resolution and if the amount of data is big enough, if you are having enough values to be representative of the population, of the performance of the population. Once that you have checked that you are having a representative sample, then you have to establish your specification limits. I have said that the specification limits can be given by the customer, or also you can define through a functional analysis. By the way, there will be a different video, another video, that I will have to talk about how to calculate specification limits using binary logistic regression or ordinal logistic regressions, but that will be a different video. Or also you can establish your specification limits based on the performance that you have had. I recommend to use virtual specification limits based on the quartiles of your data. I don't recommend you to use at all based on the process capability. And well, once that you have your specifications, then you have to check normality. If you are having few values, Kolmogorov-Smirnov. If you are having from 16 to 50 values, Anderson-Darling. If you are having more than 50 values, chi-square test. And all of those tests are if you are having good resolution. If you are not having good resolution, then you can use Ryan-Joyner test. And by the way, if you have a normal distribution, then you will calculate the PPMs using the original data. And basically based on the number of standard deviations that are there between the mean and the upper specification limit, you will calculate PPMs. The mean minus the lower specification limit, you will have the PPMs lower. And if you add together, you will have the total PPMs, and from there you will establish your sigma value. But if you are not having a normal distribution, then recommendation is to try to normalize the data. First, I recommend to use Box-Cox transformation. Find a lambda value, which will be an exponential, that when you apply that lambda value to the original data, although the original data might not be normal, the transformed data can become normal. If If you normalize the data, then you will calculate the PPMs, use the transform values and the transform specification limits. But if you were not able to normalize the data using Box-Cox transformation, you can try other much more sophisticated transformations, which are Johnson transformation. Same thing, if with Johnson transformation you are able to normalize the data, then calculate the PPMs using the transform data and the transform specification limits for the normal distribution, and based on the number of standard deviations for the transform data and the transform specification limits, you will calculate the PPMs. And from the PPMs you will get the sigma, and the sigma will let you know how big your problem is. And basically that's it for now. Thank you very much.